Wrapping up our discussion of these weak acid ice tables, we're going to talk about designing acidic solutions. So ice tables give us this, ice tables for weak acids give us this equation that relates these three variables. And we've seen that as long as you have two of them, you can solve for the third. So what we want to look at now is solving for the initial concentration of acid. And so what this kind of problem would be is I know what acid I'm going to use, and I know what I want the pH at equilibrium to look like. Right? I know what I want the pH of my solution to be. So what concentration do I need to make my acid? Right? What concentration do I need to make my solution in order to achieve my target pH? And this is a bit more higher level and a bit more kind of design of solutions, right? Where you know the acid you're going to use, you know the chemical you're going to use, you know the desired properties. How can you prepare a solution with that? It's a bit more forward thinking than our other calculations, which are a bit more reactive. I have this solution, what does it do? And so this is a bit, but kind of a bit more application, but it uses the same kind of base mechanism of this equation that comes out of the ice table when we look at a weak acid in water. Let's do an example. What concentration of hydrofluoric acid is required to make an aqueous solution with a pH of 2.09? So I know what acid I'm going to use. I know what I want the pH to be. What concentration of acid do I need to start out my solution to have? So what concentration of hydrofluoric acid, which is HF, is required to make an aqueous solution with a pH of 2.09. Okay. So we have, in this case, we know what acid we're using, so hydrofluoric acid. So we can, one of the things that we can right away, we can look up what that acid is. HF, Ka is 7.2 times 10 to the negative fourth. So because we know the name of the acid, that tells us what the Ka is, how strong the acid is. So 7.2 times 10 to the negative 4 is my Ka. And we have some information on the pH. We have a target pH of 2.09. So what that tells us when we have that information, what that allows us to do is basically we have an acid, we know what acid we're going to be using, and we know what we have a target property for our solution. We want the pH to be 2.09. So the question is, well, what concentration of acid do you need to start with? How do you need to prepare your solution to yield that property, pH of 2.09, with hydrofluoric acid? And so again, we're going to use kind of the baseline idea that comes from an ice table, kind of setting everything up in that way, how we can kind of work through this. And so we know hydrofluoric acid is HF. And if we're talking about pH, we're making hydroniums. So it's reacting with water. This thing is a weak acid. So we know it's going to be in equilibrium, double arrows, H3O plus. And so what I'm going to do is I'm going to set up an ice table kind of setup. And the reason why is you'll notice what we want is the initial what concentration. When I ask for the concentration of hydrofluoric acid, what I mean is the variable that goes right here, what that initial concentration is. Now, I don't know, right? This is what I don't know. So this is going to be different than how we've previously done ice tables. I'm going to call it concentration of HF 0. Right? If you remember that 0 down there tells us the initial, or that's kind of our kind of designation, time equals 0. Previously we saw dealing with integrated rate laws. But we're going to call that the concentration, initial concentration. I don't know what it is, but I know that's like, I kind of imagine that I start a solution with only that, and then it reacts with the water to make fluoride and hydroniums. So those are 0. I'm still going to shift to this direction. Coefficients are all still 1, so it's just x, no 2x, 3x. So x, and over here it's the concentration of HF naught minus x. And so then the Ka is equal to x squared is going to be on the top because it's those two right there. Oh, we'll write out what Ka is. We'll write out the actual F minus H3O plus times the concentration of HF naught minus X. So that's that initial concentration, because what we want really is the concentration at equilibrium, and it's going to be this right here. So Ka is equal to X squared over the concentration of HF naught minus X. So we know at equilibrium it's going to be a different value, right? At equilibrium it's going to be this initial concentration minus my X, and so I want to know what that is. And so the thing is, I figured out that Ka, I know Ka because it's HF. So this is 7.2 times 10 to the negative 4. So I have a value for that variable. I want this concentration initial of my hydrofluoric acid. So the question is, do I know X? Well, we know that X is describing what the equilibrium looks like, how much the shift is. And I know that X is equal to the concentration of hydroniums, right? That's this part of the ice table right here. And similarly, that we've seen previously, the concentration of hydroniums is 10 to the negative pH. And so what I can do then is I can solve for X. 10 to the negative 2.09, because I'm given the pH, is 7.94 times 10 to the negative 3. So what this tells me is, again, I know what acid I'm using. I know what equilibrium needs to look like, what the concentration of hydronium needs to be, or what my target concentration of hydronium is. So then I can plug those values of X into this expression. The only variable I would have left is that initial concentration of HF. So if I plug them all in, I get 7.2 times 10 to the negative 4 is equal to 7.94 times 10 to the negative third, and that is squared. We don't want to forget that square up there. Concentration of HF initial, which I don't know, minus 7.94 times 10 to the negative third. And so this just becomes a process of solving for this variable. The Ka comes once we know what the type of acid is, i.e. it's HF. We know the value for Ka. We can always figure out X if we have the pH, just from using our pH relationship. We can always know what the concentration of hydronium is at equilibrium, right? This is kind of what we're trying to get at, is kind of like, how did you initially set up the reaction? And then basically, in order to reach an equilibrium with this specific amount of hydronium, with this target amount of hydronium. And so I guess if we're going to solve it, we'll go to the next page. So I get 7.2 times 10 to the negative fourth is equal to 7.94 times 10 to the negative 3 squared HF minus 7.94 times 10 to the negative 3. So I want to solve for this HF. It's in the denominator, so I need to move the whole denominator out. I can swap these. Basically, I'm just taking the denominator, I'm multiplying the whole thing out and dividing this down to be in the denominator. I want to add this to the other side. So the concentration of HF is going to be equal to 7.94 times 10 to the negative third squared over 7.2 times 10 to the negative fourth plus 7.94 times 10 to the negative third. And I get that the initial concentration of HF is equal to 0.10 mole. And so that's doing algebra. But again, we're using the ice table kind of format to set up what the algebra problem looks like that we're trying to solve in order to get this initial concentration of hydrofluoric acid. This is kind of, what would the label, if you called it 0.10 molar, we know at equilibrium, that's not the actual concentration because some of that's going to react out, right? Some of that will react to produce hydroniums. And so that would be kind of the initial concentration. And then you would, from that, you would have enough reaction with water to produce your target pH of 2.09 if you use hydrofluoric acid. And so we can start to use, the ideas of acid-base chemistry to, kind of guide how we prepare solutions. I want a specific pH, right? I want pH of 2.09. Now, what sort of solution of acid do I need, right? Go pull out my hydrofluoric acid. I'm going to be, preparing my solution, doing a dilution or whatever it is. I now have a target concentration, and I can figure out what concentration I need in order for my solution to have target properties, which is really kind of how, really being chemists is how can we prepare a solution with the properties that we want instead of just kind of diagnosing, all right, I made a solution, what's the pH? Let's try another. What concentration of HI, that's hydroiodic acid, is required to make an aqueous solution with a pH of 2.09? On face, this looks very similar to the last problem, but let's dive in and see that this actually is going to be a different, going to require a different approach and kind of show some of, inform why and how we prepare actual acid solutions in the lab. All right, what concentration of HI, so hydroiodic acid, is required to make an aqueous solution with a pH of 2.09? So similar idea to what we saw previously. I have an acid I'm going to use, hydroiodic, and I want a target pH. So the question is, what concentration do I need in order to reach my target pH? And it's, you'll note, the same one, 2.09, that we saw previously. And so if we think about, well, we can kind of go to look to set this problem up. So the HI changes the pH by reacting with water to produce hydroniums. So HI aqueous plus H2O liquid. But now when we think about this, we want to be careful. HI is a strong acid. It is on our list of 6 strong acids. Hydrochloric, hydrobromic, and hydroiodic are all strong. Basically all the halogens except for fluorine lead to strong acids. And so this is a single arrow where we then get the conjugate plus hydronium. So we sometimes kind of get a little overzealous. If everything is weak acid, weak base problem, throw around ice tables. We don't need to use ice tables. We know we can use stoichiometry, and we know that the concentration of hydroniums in this solution, which we could say is like at equilibrium or after the reaction happens, is going to be equal to my initial concentration of HI, right? Whatever that initial concentration of HI, all of it reacts and creates hydroniums. And so we know that the concentration of hydroniums is equal to 10 to the negative pH. So that tells me the concentration of hydroiodic acid that I need initially is 10 to the negative pH, 10 to the negative 2.09. We saw this previously when we were dealing with HF. And that tells me that the concentration of HI that I need to set up is, if I solve that out, 8.1 times 10 to the negative 3rd molar. I'm just doing fewer sig figs here compared to the last one. 0.081 molar. And so this also goes to show why we use strong acids when we're trying to prepare solutions like this. Even just trying to figure out, oftentimes we want a target pH. I need a solution with pH 2.09. 88.46, 12.32, 1.4, whatever the pH that we want is, figuring out the concentration of strong acid that we need to use is going to be much simpler, right? No ice tables required. It's just figuring out the concentration of hydroniums from the pH, so just using that one equation, and then we can read it all out. And that's all we need to do for this process. It's much more straightforward, and that's one of the reasons why we use strong acids, strong bases when we're dealing in the lab to prepare acids and base solutions and using those sorts of things. We'll see, maybe sometimes we can't, we need to use weaks, But in this case, if we're just trying to make a solution with the target pH, using a strong acid is going to be easier. It also requires a lower concentration, and you don't have any excess acid floating around in solution. It's all turned into hydronium. But I do want to note, on the last example, when I did this process, I kept more digits. I didn't round as aggressively. That's because I was solving it as inside the problem. This answer should only have 2 sig figs, and so that's why I'm going to 2 sig figs here. It was an intermediate value, so I was waiting to round until the end. That's why I used more digits when I was writing it out on the HF problem. But here, we only need the 2 digits. That should be the appropriate sig figs. I don't want to worry too much about sig figs with logs and 10 to the inverse, as long as you're rounding somewhat. But that's just why I'm doing it differently here. So if we look at these 2 examples, in both cases, our target pH was 2.09. But we can see that the necessary concentrations of acid, that initial concentration, how we would prepare the solutions were different. We can see with HF, we needed 0.1 molar, whereas with HI, I only need 0.0081 molar. So I need a higher concentration of HF, which is indicative of the fact that it is a weak acid. HI is a strong acid. I don't need a huge concentration in order to get that same exact change in the pH and to get that shift away from neutral. And so there's a couple things that come from this. One, it's just more efficient to use strong acids, right? It is more efficient to use strong acids to change the pH of a solution. You don't need to use as much of them. The calculation to figure out what concentration of acid you need is more straightforward. That generally makes it a little more advantageous to use, easier, less error prone. The other big thing is that when you have this HF solution, there's still a bunch of extra acid in there. And so that extra acid can react. It doesn't react with water in the case of changing the pH, but it is there, and that makes it a little more dangerous, right? There is more acid in that solution. So if we can avoid it, we don't use weak acid. If our only goal is change the pH of the solution, we're going to use a strong acid. It's more efficient, it's easier to figure out, and it's a safer solution. All right, that's another video down. Looking for more questions on participation 1014. See you in the next video.